Hi, so I'm going to teach you all about Euler's method. Now, Euler's method is a really useful tool for approximating values of functions that you can't find algebraically. And let's do an example for that. So let's say you have an equation for a derivative. You have dx over dy equals 2x plus 3y. So that's how the slope, that's how the derivative changes across the graph, but you don't know what the function looks like. And let's also say that f of 2 is equal to 4. That's a point on the graph, that's a given. So how can we approximate a value using this information? Let's try to approximate f of 5. And for the purposes of this problem, let's use a delta x, a step size of 1. Now, to make your approximation more accurate, you can lower this delta x, you can lower the step size, but the more steps you have to do, the more accurate your approximation becomes, but the more work it becomes and the more chances for error in your work you can have. So let's set up a table of values of x, y, and dy, dx. And we have this given value of at x equals 2, y equals 4. So let's plug in values here to determine what the slope is at that point. So it's 2 times 2 plus 3 times 4, which is equal to 4 plus 12, which is equal to 16. Now let's keep our approximation going and increase our x value by 1. Let's find an approximation for this function at x equals 3. Now, so this is the slope at the point x equals 2. So if we assume that slope is constant until we reach the point x equals 3, which is not accurate to how the function works, but this is for the purposes of the approximation, this is how we're doing it. So if we assume that, then we would increase our y value by 16 because our step size is 1. So at x equals 3, we can approximate the y value to be 20. Now, we can't just continue to use this same derivative, the same slope across the whole approximation, because that would approximate it as if it's a line. That would be a very bad approximation because it would just be a line. So let's plug back in this x and these y values and the derivative to find out what the slope is at that point if this is a point on that function. So it's 2 times 3 plus 3 times 20, which is 6 plus 60, so it's 66. So our approximation for the slope here is 66. Okay, so let's do another step. Let's do Euler's method again. So let's increase this to x equals 4. And since our step size is 1, we increase the y value by 66 because the slope until there is 66. So the y value at 4 we approximate to be 86. And let's get another derivative to improve our approximation before the final step. So it's 2 times 4 plus 3 times 86. And 3 times 86 is 258, plus 2 times 4, which is 8, gives us an approximation of the derivative at this point of 266. And moving forward one more step, to x equals 5, we add 266 to the y value because that's the slope and we're increasing by 1, and the slope is 266. And we approximate this y value to be 352. So that's our approximation. That's the approximation of this graph. It's not a perfect approximation. If we wanted to improve it, we could decrease the step size. But using Euler's method, this is the approximation that we get. So I have plugged in the values that we just calculated as if they were equations in point-slope form in a piecewise equation to create this general approximation of the curve. You can see that it's not very smooth since we had such a large step size of 1. This approximation is not very accurate. You can use a much smaller step size to get a much better and more accurate approximation of this curve. So I took this and I made an approximation using a step size, a delta x of 0.25. I only did it up to 4 because it's a lot of work. There's a lot of values, and I took that and I used it to create equations for lines that I plugged into Desmos to visually see how the approximation using the smaller step size and the larger step size compare. So the black curve is using this larger size. It has the 3 points converted into an equation in point slope form to show this approximation of the curve that we were using before to find that first value. While this curve here in red is the curve of the using the step size of 0.25. So you can see that this curve looks a lot more smooth, which it's a much more accurate approximation of the curve. So if this delta x approached 0, you would find the equation for that curve at when the limit of delta x approaches 0. So that's Euler's method. Let's review what we did. Let's go over what Euler's method is. So Euler's method is a way to approximate values of a function. You can use it to approximate a curve based on an equation representing the derivative. Yeah, so the equation representing the derivative is the slope, because it's the change in y over change in x. That's what the derivative is. So essentially this derivative can be used for approximation in a case where you can't find an exact algebraic value for the function. Euler's method is a way to make an approximation using this slope, this idea that the slope changes, and plugging in numbers, and a smaller step size is a more accurate approximation. So that's very similar to Riemann sums and other ways of approximating things using similar techniques of making step sizes and to find approximations. So thank you so much for watching this video about Euler's method. I'm hopeful that I can make more content like this in the future. perhaps I'll just start uploading for fun, for my massive subscriber base. Thank you so much.